millimeters. Anybody who reached number 4? 10 points, yeah, 10 millimeters. That's the number that I wanted to get. Okay, let's solve number 4. So we're looking at the thickness of the pressure vessel. So here we're going to use the von Mises stress because we're only given the yield strength. We're given a factor of safety of 2. So our design will be based on the von Mises stress. So if I wanted to write first my equation here, I have now my working stress, okay, or my yield strength divided by, so my working stress is equal to that yield strength divided by 2, or my design strength is equal to that yield strength divided by that safety factor. So I'm going to equate that von Mises stress to that yield strength divided by a safety factor. So this one is 370 megapascal divided by 2. So I have now here 185 megapascal. Okay, so that's my target now. And if I have my equation here, this will be 1 over square root of 2. I'm still working anyway on a pressure vessel, so there's no shear here. Okay? So I still have my sigma 1, sigma 2 squared plus sigma 2 minus sigma 3 squared plus. So there's no shear here for pressure vessel unless it's stated that you have the so-called torsion or shearing stresses. But at the moment, if we're just looking at pure cylindrical pressure vessel with only the stress based on that internal pressure, then we're just looking at normal stresses, which are actually the principal stresses. So in this case, we don't have sigma 3. So that will be 0. We know that your sigma 1 is actually your hoop stress. We know that your principal stress for pressure vessel is actually your hoop stress, your first principal. So this will be your PR all over T. And you know that your second principal is your longitudinal stress, which is PR all over twice the thickness. Now we only have P, and we're supposed to know T. So this one has a value. Okay, this should be equal to that 185 megapascal. So here, of course, we have now your volume equal to pi r squared multiplied by that height. So we're looking at a right cylinder. Well, the tank's supposed to have that thing there, okay? So it's that spherical end, which will balance the pressure inside. But to make it simple, we're going to consider a right cylinder. So this one definitely will benefit your cylinder, that spherical end there. But for simplicity, we just consider a right cylinder. But never, if you're going to design a spherical, or you're going to design a pressure vessel, never design it or never use a right cylinder. Okay? Because there will be, just an addition here, if there will be stresses in there, or pressure. Okay, just an example. At this corner, you will have that resultant pressure there, which will be very high. That's why you use this spherical end to balance or to distribute those pressure. Well, I've had first-hand experience of having this one, so we have to repair it and change it to this one here. Okay, so it happens. I mean, it can cause accident, but we're lucky that nobody was there then. So, okay. So moving on. So we have the H, we can get the R, yeah? V all over R squared is equal to pi H. So what do we have? So the volume is given to be yes, 0.012 cubic meter pi, and you have the height to be 0.47 meter. So you have this one to be in meters squared. That's R squared, so you will be able to get R in terms of meter or millimeter, depends on how you work. So R will be, my case is 90 millimeters, approximately. So I have this one to be 90 millimeters. Okay, just round off. Okay, next. So I got R. So I have P, I have R. So now it's just the thickness, yes? So I think we had a similar problem last time. We're just going to substitute the values now. So this one is 185 megapascal. So I can just multiply this one with the square root of 2 now. And then I have this one to be PR all over T minus PR all over twice the thickness squared plus PR all over 2T plus PR all over thickness squared. I think I made a mistake here last time, so please check my math there. I really failed. It was a Thursday, so. Now, still a Monday, but I'm still making mistakes, so it's a Monday, so. It's week 9, so I'm a bit tired, you're tired. You're tired too, so. Let's work on this one. So I have this one to be PR all over twice T, yes? This one, and then plus PR all over twice T squared plus PR T squared. So I have, okay, so again simplifying this one, 2PR twice T squared plus PRT. So I hope I'm correct now. So I have this square root of 2 here and 185. So please take note, we're working in megapascal. So if this one will be in millimeters, so this should be in Newton per millimeter squared. So please check me here. So this one now will be 2 multiplied by, what do we have for P? So we have 24 megapascal or 24 Newton per millimeter squared. So I'm just trying to be consistent with the units. You can ignore them if you're very familiar. So your radius will be, my radius will be 90 millimeters. And then I have here twice the thickness. Yeah, actually, we can further simplify this one, yes? Just leave it. So I have this one to be 2 multiplied by the thickness. So that must be squared. Okay, so as you can see, I'm quite consistent with my units. If I'm working on, if I'm using millimeters and Newton, then I should be consistent with the other side as well. So what I'm going to get here will be a thickness in millimeters. Okay. So please carry on with the simplification. It's more algebra. So what you get here will be 10 millimeters. What textbook are you using for mechanical design? If you're using Shigley, then all of this should be there. Yes? So, I think in a way, some of them definitely will be related to mechanical design too, because you relate the actual situation to the concepts of theory of elasticity, plasticity, and so on. Okay? So please carry on with this one, and if you have any queries, let me know. Send me an email. Next meeting, we're going to do a derivation on the pressure vessels, as well as the limit state. Do you have any questions or clarification? So, again, we're just practicing, or we're just applying all the concepts that we learned from the notes that we have. So if you have any additional suggestions on how we proceed, well, I'm always willing to take note of that. Okay? Questions, corrections, clarifications? If there's none, then thank you very much for coming.